Okay, I want to give you the algorithm for the Newton divided difference. Okay, so for Newton divided difference, you need to know n, which is the number of values. So n, okay. Then you need to know your x naught, y naught, x naught, y naught. Well, yeah, x1, y1, all the way up to xn, yn. That should be a capital N. And let's make this a little n, then I don't have to. And then, so this is where you can make a vector x, which is going to be zeros. N plus 1, 1, and then y is actually, I'm going to call that, I'm going to call it y. I'm going to call it y. Zeros. N plus 1, 1, and then here your x at I is equal to xi, and your y at I, you'll do a loop, is equal to the f of your x at I. So that's your input, okay? And your output is going to be the numbers f naught, f00, f1, 1. I think I called these D, so let me just call them D, because I was calling them D's. So I'll keep calling them D's. D00, D11, D22, all the way up to DNN.
Excuse me, ma.
Yes.
This algorithm is for
The Newton, this is for the Newton divided difference.
okay.
So we were working on the Newton divided difference when we had to do the table, and then we pick off the one straight down the column.
Yeah.
And then those are the coefficients of the polynomial.
Okay.
Do you remember?
Yes, yes.
Okay. Okay, where my Pn, this is my polynomial, is actually equal to D naught, D00 plus the sum of I equal 1 to N of, of DII times the product of J equals 0 up to I minus 1 of the X minus XI, X minus XJ. Okay. And again here, D at II is equal to F at X naught all the way up to XI. All right, so here's the algorithm. So the first thing you do is for I equal 1 all the way up to n, and for j equal 1 all the way up to I. You let d d ij is equal to d I j minus 1 minus d I minus 1 j minus 1 all over xi minus xi minus j. And then you do that loop end, and then you can output your f, your d 0, 0, d 1, 1, all the way up to d and n. And then you can do your loop. After this point, then you just need to compute what your Pn is. All right, so you would set up a loop that would do your product, multiply by your D, and now D0, 0 is simply F of X naught. And so D0, 0, so I should have defined that at the beginning. D0, 0. It's F of X naught. Okay. So that's the Newton divided difference. Okay. And that works very nicely. And I did the one for the interpolation for that. And let me see. I did the summary. Okay. So the error So the error in interpolation is the same as the error for the Lagrange interpolating polynomial. So E of X turns out to be X minus X naught, X minus X1, X minus Xn, n plus first derivative at some number C over n plus 1 factorial. And that you can compute provided that you know what the function originally was. Okay. All right. I'm not going to do this because of time, but we have a Newton forward divided difference formula. You know how to do the Newton divided difference formula. The Newton forward divided difference formula is very much the same. The only difference is it really is a pain to write out. But why would you use the Newton divided difference formula? Okay, you would use the forward divided difference formula. So you use this formula. When computing, when approximating f of x for x naught less than x less than xn, and x is close to the end of the tabulated values. I don't feel like I'm recording. Am I recording? Oh, I'm recording. I just don't remember doing it. And then there's a Newton backward divided difference formula. And you use this formula. I'm surviving. Yep. I don't need pain meds. I'm just no. I can see. No. When you're approximating f of x, again, x naught is still in between there, but x is now close to the forward, to the beginning of the tabulated values. Okay. All right. Okay. So the third polynomial interpolation we want to use is cubic splines. Okay. So again, we're still doing polynomial interpolation for a set of n plus 1 points.
Excuse me.
Yes.
The Newton for divided difference formula. Is it just in book? No algorithm for that.
So I'm only going to hold you responsible for the first one that I did, the general one.
Okay.
Yeah, I'm not going to hold you responsible for the forward or the backward. If you ever wanted to use them, they're in the book for you to do as a reference. But you need to know the general one that I did. Okay. All right. X, K, Y, K. K equals 0 to n. So this is often unsatisfactory. Okay. So sometimes you'll get, so you may have something like this, and you have maybe a point here, and a point here, and a point here, and a point here. And so this is going to have to be a cubic polynomial. All right, so n plus 1. So here, n would equal 3, which means you get P3 of x using Lagrange. Or Newton. And so who knows how it's trying to fit everything into this polynomial. So for example, it could go up like this and then come down like this. No, it won't. I'm trying to think how we'll do it. This is cubic. Yep, that's wrong. It would have to do something like this. And it could actually, okay, so that could be the polynomial that it comes up with. And so actually, the value that if you were to interpolate this value right here, with x is equal to 0, suppose this value may actually be there, but the polynomial is, because it's a polynomial, would actually put it right here. So the polynomial, if I was to try to figure out what the value is I'm interpolating, and I'm trying to figure out what the value is at that x point where the green dot is, if I use the polynomial, because it's got 4 points, it created a cubic. So the cubic it created may look like that, but the problem is that the value may be very far off. Okay. And so this polynomial of degree n, I'm trying to think, do I use capital N or do I use small n? Does it matter? I think I use capital N. I don't like capital N, but I better use it because that's what's in my notes. Okay. Can have n minus 1 relative maxima and minima. So it's actually better if we piece together the graphs of lower degree polynomials. So we're going to call them SK of X. Okay, so let's say we're on, here's my line. And I have X0, X1, X2, and then XK minus 1, XK, XK plus 1, and then over here, I have XN minus 1, XN. So if I create polynomials over just smaller regions, so maybe I had something that maybe looks like this for that piece. And then maybe this comes out and goes there, but now I have another polynomial that's just over that piece. And then maybe there's a polynomial that just goes over that piece, as opposed to trying to do one polynomial that's going to satisfy everything. Because this one polynomial, if you look in this picture up here at the top, that one polynomial has to go through all those points. It has two maxima, one minima, and that could actually cause my interpolation to be very poor. Okay, so let's look at piecewise linear interpolation. We already know how that works, but I'm going to do that. Oh, I didn't mean for that to be red. I want that to be, oh, come on back to cubic splines. Okay. So let's look at piecewise linear interpolation. Okay, so piecewise linear interpolation is we're just going to take and put lines between every point. Okay, so we've seen that before. So that means we have a polynomial of degree 1. And so this polynomial of degree 1 and it consists of line segments that pass through the points. And this is the same basically as that linear interpolation. So that means on any interval xk, to xk plus 1, sk, that's the line on that interval. Well, let's just use the Lagrange interpolating polynomial. That's going to be x minus xk plus 1 divided by xk minus xk plus 1 times yk plus x minus xk divided by xk plus 1 minus xk, and this is yk plus 1. So you guys should recognize that as the first Lagrange interpolating polynomial on the interval xk to xk plus 1. And so that's very simple. That says that here's my graph, and at my points x0, x1, x2, x3, all the way up to xk, nope, xn minus 1 to xn, whatever my points look like. I'm simply going to draw a line. So that's S1. That would be S2. Actually, I'm wrong. This one is S0 of X, and this one is S1 of X, and this one is S2 of X. Okay. And then down here, this one would be Sn minus 1 of X, where each one is linear. And as you can see, if I put in xk in sk, so sk of xk, well, you put in xk. When you put in xk, the first term is going to drop out. No, the first term you put in xk, you just get yk. And then sk of xk plus 1 is simply yk plus 1. So it gives you what you're supposed to get. Okay. So instead, what we want to do, so that's what we do for linear. And then you guys know how we did the polynomial interpolation. I'm sorry, the quadratic interpolation. So now I'm just going to skip the quadratic and go for the jugular. So I'm going to go to piecewise cubic splines. Okay, so these were linear interpolations. Now I want to go to piecewise cubic interpolations, but we're going to call them splines. And the reason why they're splines is because they have something else besides just the basic problem. So piecewise cubic splines. Okay, so this now is, we're going to construct cubic splines. Okay. Here's xk. Okay, so this is the spline. This is sk of x, and this is the spline. This one is sk plus 1. Okay, so now you can see that sk at this point has to be xk plus 1 at the same point in order to make it continuous. All right, so we defined our S as such. Then we said the splines actually have to go through each data point. Then they said they have to be continuous. So that's we have n minus 1 of those conditions. Number 4, the first derivative has to be continuous. So that means sk prime at xk plus 1 has to equal sk plus 1 prime at xk plus 1. Okay. That's true at k equal to 0, 1, all the way up to n minus 2. So now there are n minus 1 of those conditions. And that says the first derivative of s of x is continuous. Okay. One more, number 5. Second derivative. So sk double prime at xk plus 1 has to equal sk plus 1 second derivative at xk plus 1. And again, for k equal to 0, 1, all the way up to n minus 2. So this is n minus 1 constraint. Their question?
The first condition and the second, is it for any kind of function? Must it be continuous? Like you specified on third and fourth, that is continuous function.
So we are taking and we're creating a cubic polynomial going from one point to the next point.
Okay.
A different one from x0 to x1 is going to be a cubic equation. From x1 to x2 is going to be a cubic equation. From x2 to x3. So each one has its own cubic equation on each interval between the points. But we're making it so that anytime you're at a juncture where S1 meets S2, it has to be, the first derivative has to be continuous. The function has to be continuous. The first derivative has to be continuous. And then the second derivative, its concavity has to be continuous. So that's what we're doing. So that's where we get all these different things.
Oh,
Okay.
okay.
So this one says the second derivative okay. So now that gives us n plus 1 plus n minus 1. Actually, I'm going to make life easy. There's 3 of them. Equations. So that is equal to 4n minus 2 equations. But the problem is we have 4n things to solve for. So we have n cubic polynomials sk of x. Each of them has 4 unknowns. So that gives us 4n degrees of freedom. Jose, I meant to say 130. He's coming. Okay. So we have 2 additional degrees of freedom that we have to deal with because we have 4n unknowns, but we only have 4n minus 2 equations. So we have 2 additional degrees of freedom. And with those 2 additional degrees of freedom, that gives us the chance to do endpoint constraints at x naught and xn. Okay, so everybody understand what's going on? We only have 4n minus 2 equations, but we have 4n things to solve for. So in order to do that, we're going to have to put endpoint constraints at x naught and xn for our polynomial. Okay, so this is the construction. All right, S of x is piecewise, is cubic, piecewise cubic. So therefore, the second derivative of S is piecewise linear. So the second derivative is piecewise linear. The first derivative is a piecewise quadratic, and then the function itself is a piecewise cubic. Okay, so let's start off from the base under the bottom. So we're going to start off with the second derivative being piecewise linear. So that means the second derivative, sk of x, has to look like this piecewise linear function that I originally had done for s itself. The difference is I'm now going to do this for the second derivative, because the first derivative is cubic. So the second derivative, the first function is cubic. So therefore, the second derivative is piecewise linear. Okay. So we need to find s of xk. That's the second derivative of xk. And now I need it to be linear. So I get x minus xk plus 1 divided by xk minus xk plus 1. And then I'm going to add it to s double prime at xk plus 1. And then this is going to be times x minus xk over xk plus 1 minus xk. Okay. All right, so now what I'm going to do is I'm going to call this mk. God, I'm almost over. Okay. This is negative hk. That's the distance between any 2 points. Then this is going to be mk plus 1. And then this is going to be positive hk. Okay. So now I'm going to write this as the second derivative of sk at x is now going to be I don't like the way that looks. That part is minus hk. And that part is positive hk. Okay, now it looks better. So now I'm going to get mk divided by hk, this term, and then I'm going to make it hk plus 1 minus x. And then I'm going to add to it mk plus 1 over hk times x minus hk, xk. Okay, so now that I know that my second derivative is piecewise linear, that's what I get. Okay, when I integrate this thing, all right, I'm going to integrate okay, so when I integrate this thing, I get sk prime. Okay, so now when I integrate this, I'm going to get xk plus 1 minus xk squared. Then it's going to be over 2 hk. And then I have to deal with the -1, so that gives me minus mk. And then I'm going to do the same thing with this next term. I'm going to get xk, x minus xk squared. This is also over 2 hk, but this just stays mk plus 1 because I don't have a negative to deal with. And I get my trusty little constant C1. Okay, let's do it again. So when I do it again, I now get sk of x. So now I'm going to take and get xk plus 1 minus, this should have been an x, not an xk, minus x. This is cubed. So now I'm going to get a 6 in the denominator. And my negative is just going to give me mk. And then here, I'm going to get x minus xk cubed. Now I'm going to put a 3 in the denominator. So I'm going to get 6 hk. And then I'm going to get mk plus 1 plus c1x plus c2. All right. Now, I'm going to take this c1x plus c2, and instead, I'm going to write it as such. So this c1x, this part, so I want to write c1x plus x2, that's, c2, that's just some linear function. And I can write it any way I want. So I'm going to write it as pk times xk plus 1 minus xk plus qk times x minus xk. So as you can see, it's still linear. I just like to write it like that. It's much better. All right. So obviously, we got to figure out what P and Q are. And so now we get this whole thing. I hate that. Plus pk xk k plus 1 minus xk plus qk times x minus xk. Okay, so now I know what my kth cubic spline looks like. So now if we substitute xk and xk plus 1 into sk of x and use the fact that yk is equal to sk of xk and yk plus 1 is equal to sk of xk plus 1, then we get something really nice. So then we get that yk is equal to mk over 6 times hk squared plus pk hk, and we get yk plus 1 is equal to mk plus 1 over 6 times hk squared plus qk and hk. And with those two things together, we can solve for pk and qk. All right, so now that's known. Okay. All righty. Oh, shucks, we got 1 minute. Okay, I'm going to stop here. Uchenna, I'm going to need you to log off so I can give Yibing and Kayla the password to the test.
Okay, ma'am.
All righty.